We are very happy to have you today for this BIMXT session. My name is Dana DeFilippi, coming to you from the Washington, D.C. area. First presenter is Seonhee Kim, coming to us from the Design Collective. And she's going to talk today about some really awesome tools. Thank you, Seonhee. How are you today?
I am doing great. And let me get this thing ready and go.
Awesome. I see it. It looks great. You want to tell everybody a little bit about yourself and where you're calling from today?
Yes. Hi, everyone. My name is Seonhee Kim. I'm a director of sustainability here at Design Collective. Design Collective is an interdisciplinary design firm, architecture, interiors, urban planning, landscape, graphic design. The physical office location is in the Baltimore and the Chicago. And right now I am in my Baltimore office. So let's go. I have a lot to cover, but at any point, if it's getting too long, then just cut me off. So today, the topic that I'm talking about is my favorite. It's a carbon teaser, choose your own carbon adventure. So we're going to exclusively talking about carbon. And okay, just click. So why AEC industry should pay attention to carbon? Because we touch too much in the process of carbon emitting the segments. So that is why it is really important for us to talk about it. And why now? I think everyone is aware of the concept of the time value of carbon. The response is always delayed. And right now is really, really important time that we reduce our the carbon emission. And a lot has to do with actually building the physical building associated with the carbon emission. So that's why we are our enhanced attention goes to the embodied carbon section of it. So the stage of carbon, when we talk about carbon, it encompasses the gamut of all phase and processes involving the carbon emission. So you can kind of see the production phase, construction phase, maintenance and the usage phase, end of life, and the recycle. And these are considered the module. And out of these A1 through D module, only B6 and B7, these two segments are operational. Historically, the AE industry and the entire world has been really, really focused on the energy efficient building. And those are related to the operational carbon without considering the entire scope that is involved in the AEC industry. So now is really, really important that we kind of start to finish on the carbon emission related to the building industry. So tools that we are going to talk about as a teaser. So these three are mainly involved in geometry. So the TallyCAT and the COVE tool and Total Carbon Insight Tech Review is a three main items that I'd like to touch on today related to the geometry. So TallyCAT is developed by Building Transparency, C10G Lab, and Perkins Will, and it has a very similar the method and way of approaching carbon as a Tally. And this is a free Revit plugin, and the link that I provided in the mural, you can go and then actually download the TallyCAT plugin. And the actual meat of the database is utilize EC3 database to calculate the embodied carbon and the carbon reduction opportunities. COVE tool embodied carbon is the new feature that is rolled out early this year. It is developed by COVE tool and it is subscription based. So COVE tool user can access it. And it also uses the EC3 database to calculate the embodied carbon. And their focus is A1 through A3 stages. And they have a plan to include and enlarge its scoping. Total Carbon Insight Tech Review, I wasn't I didn't think this would be ready for today, but it just released as the beta for the public in 2 or 3 weeks ago, maybe a little longer than that. But it is developed by Autodesk, and it is Revit plugin, included in your Revit subscription. And it uses the EC3 and Autodesk custom value to calculate the embodied carbon. And currently available scope is only for the exterior OPEX assembly. If you have time, then I'll go over the CoveTools and Kaleidoscope. Those two are the web-based calculator or assembly assessment tool that is developed by various architecture firms. Payat developed the Kaleidoscope and generously open access to anybody. And CoveTools is developed by the Siegel Strain architects, Goody Clancy, and Architecture 2030. So going through the workflow, the TallyCAT workflow is starting from the geometry prepared by Revit, and it is a detailed model, and then using the add-in, the TallyCAT, and it is a connection tool that the model to the EC3 website. And data mapping happens in the EC3, and it is all the collected EPD information on the EC3 website that is going to be assigned to the actual material. So the material takeoff happens using the Revit model, and the actual database coming from is mapped through the EC3, and the result can be displayed either EC3 platform as well as back in the Revit. And from here, this is kind of the important feature that using the Revit library function, they can actually connect between those two platforms, that whatever is mapped in EC3 can be developed into the Revit library as a family, and then it can be reused into your new Revit model that you're going to build. So that is the same idea as a Tally that has offered. So EC3 website, once you create the connection, then EC3 website, you kind of start from the inputting all the model information, location information, the scope that you want to address in here. And then it'll show all the material based on the Revit family structure. And from there, you can use the EC3 tool to assign any of the material. And from their output, you can kind of see individual. So this is a view from the Revit, and these are the chart and the report that is available on the EC3 website. And then this is a Revit library input. So under the TallyCAT, there is a function called the Revit library. This is a function that connects either dumping down to the EC3 as well as from EC3 bringing back to the Revit library. The CoveTools workflow is a little different. So it starts from creating the project on the CoveTools website. And from there, you have two options. One is a geometry is prepared by Revit detail model, and it links to the CoveTools website through the CoveTools plugin, or you can start building your building using the drawing tool. And in the drawing tool, so either you upload the geometry using Revit or building from the scratch in the drawing tool, you have to use Assembly Builder to assign certain specifics on your exterior wall. And then from there, you can use the directly go to the Embodied Carbon tab, and there you can start assigning the embodied carbon, the material specifics. And the result can be viewed in the CoveTools platform only, and iteration only happens within that platform. There's no going back to the Revit unless you make the Revit model change, and then starting from here, that re-uploading your model to the CoveTools platform. So these are some of the views that you start putting the project together using the geometry, and from there you go to the tab at the very bottom. That is a carbon embodied carbon, and from there you can assign the structure system, substructure system, exterior, and then interior. And it also uses an EPD library that is based on the EC3. And from there, you can actually pick and choose the established baseline and the opportunity that could go low in the embodied carbon. And then the third is total carbon inside.
I don't know that, unfortunately, we have time for the third, sadly. I know that our next presenters are going to show a little bit more information about Insight and CoveTools, but we would definitely love to have you back as well to show us. It looks like you have so much information to share. I've also went ahead and shared all of those tools and their links right there under your section there. So those of you guys who are joining us, since I've given my little mural presentation there, you can see under Seonhee's area, we have TallyCAT and Insight, Care Tools, and the Kaleidoscope. So check those out. If there's any others that you'd like me to add, Seonhee, please let me know so that people can get to those relatively easy. For those of you guys who are just joining us, please feel free to start adding questions. It looks like we have one here. Can multiple reports be generated with EC3 and TallyCAT to track the impact of design changes? Seonhee. As we go along, we can have the presenter essentially just comment on to our different questions. So thank you so much for that question. As you can see, those of you guys who have not done this before, we have different little icons that represent your different discipline. You can see the discipline legend here. I'm BIM or IT, so I would use the little computer and copy over or drag over the information to share. Maybe you have a fantastic sustainability tool we're not talking about today. We'd love to hear about it. Go ahead and throw that in here. Maybe you have a question for one of our presenters, as you can see from these shared, or please, at the very least, share your location and name so that you have a chance to win a prize next meeting. So without further ado, we'll move over to our next presenter, Hans Stroven with McMillan, Pazdan, Smith. He's going to talk a little bit about the Insight tools. How are you today, Hans?
Good. I'm doing great today, Dana.
Thank you. Thank you so much for joining us. Do you want to tell everybody a little bit about yourself while you're getting looks like I got your share already.
Yeah, so my name is Hans Stroven. I'm with McMillan, Pazdan, Smith, and I'm the BIM manager, one of the BIM managers here. Just a quick overview that McMillan, Pazdan, Smith is a Southeastern-based architectural firm. We've got offices in Georgia, South Carolina, and North Carolina, and I'm based in the Charlotte office. So today I'm going to be talking about Autodesk Insight. It's built into Revit itself. It's worked with both Revit and Formit, but today's focus is going to be on the operational carbon side of things and not the embodied carbon, because that just got released a couple of weeks ago, as we probably stated, and we're just getting into testing that side of things. But Insight, it's a energy simulation platform to guide and to show different scenarios that you can do within your building. Getting real-time feedback, you're able to plug in the location of it, set different standards, dial in your energy factors, and then reviewing the benchmarks via the ASHRAE 90.1 and the Architectural 2030 benchmarks. And then you're able to really dial those energy factors in to get predictive outcomes for what your building is going to behave as. And then, of course, you can then add in your members and then share with your stakeholders for informed decisions throughout the design process. So getting into this, you can start it within like your beginning stages of your site studies, doing prelim PV calculations throughout your entire building design, when you get your MEP systems inputted in, and then, of course, during project closeout, and then throughout all the different life cycle stages of your project as well. So it's really a tool that you can review and assess at different milestone markers and whenever you need to throughout your project's life cycle. So we're going to go through the toolbar itself to begin off with. You can find this on the Analyze tab within your Revit ribbon. So first, you're going to plug in your location. This is going to specify the geographic location of your project. Then we'll dial in some of the simple or basic energy settings. From there, we can then create our energy model, and this takes the three-dimensional model and divides it up into surfaces that will actually then push it up to Insight, which we'll create with the generate, and this creates our analytical model and pushes it up to Insights or Autodesk Insights web platform that will then be able to then optimize and access our energy levels and environmental performance on there. So once again, to begin off with, we're going to set our project address. This can either be a physical address, or you can just have the basic of whatever your city and state is. And then we'll want to select our weather station. So you can see that red pin is where the project location is at. And then the orange pin is going to be your weather station of what you have selected. To note with this is you'll want to select, or preferably select, any weather stations with the 59 in front of it. These are usually associated with airports and just have a little bit more current data. But like a lot of our projects are up in the Asheville area, so the mountain region, and your project could be on the top of the ridge line, or it can be in the valley below. So in those type of circumstances where you have more extreme environments, where weather patterns could be different if you're at the top of the mountain or if you're in the valley, you'll typically want to select the weather station that is most closely associated to your project location. So once we've got our location set up, then we can start dialing in some of our energy settings. Most of these are set by default, but going through these, you'll want to set this to the first mode will be set to conceptual masses and building elements. And that way we can capture both our model geometry and if you have any massing models in there too, because it will pull data from both ends of the spectrum. Level 1 for the ground plane, that's set by default, but if it's anything different, you'll want to update that information. The perimeter zone divisions, this is great for doing prelim modeling. So if you have massing forms in your project, this will set the offset. Like, so let's take, for example, you have a large office building. It will set your zone divisions. It'll give you your core of your building and then your perimeter zones. But if we already have a model building in place and we're doing the energy analysis based off from the model geometry, you'll want to go ahead and uncheck that. And then getting into the advanced options, the detailed model, this is associated once again with our massing. So it will take the percentage of glazing, what your sill height is, and some other factors in there to make some preliminary design options for you as well. But if you already got your detailed model already set up, you'll just go ahead and skip this step. And then we'll set our building type. So whatever the primary building will be, and that will take just assumed energy assumptions of that. So in this example here, I've got library set. So that'll set the operational schedule and a few other metrics in the background. So you don't have to worry about that. But that gives like a basic overview of the energy settings that you'll need to dial in just to get you going. With all of this, you can dive really into the details where you can have material properties set up for R value and U value. You can have your HVAC system set up as well, but all of that is not necessary in order to utilize and benefit from this tool either. So we'll want to then from there, once we get our energy settings set, we'll go ahead and click that create energy model. And that's going to create first your analytical spaces, which you can see all these blue boxes. It's going to carve up your building into all the different spaces or rooms of your building. And then from there, in this example video that I have going on, I'm actually duplicating this view and renaming it to analytical surfaces. And that's how I'm getting all these color coordinated surfaces that will show like the roof, the walls, the interior walls, doors, windows, and so forth. Because keep in mind that every time that you run an energy model, it's taking a snapshot of your model at that particular point in time. So if you've added or removed elements of your building, you'll want to rerun that energy model again because that's a standalone model itself that you're actually pushing up to Insight. But every time that you do that, it's going to reset that analytical spaces, but it'll keep that analytical surface view that you've set up in there. So once we've gone through and set up those basic items there, well then looking at this as a spread shot here. So it'll take it will divide your building up into like the roof, doors, shading devices, windows, the different floor types, whether that be a slab on grade or interior walls, interior floors, interior walls, exterior walls. And this is actually what's being pushed up to the Insights platform. So it becomes a very lightweight analytical model that's easy to work with, and that's where Revit is, or Autodesk is taking all of its calculations from. And then there's a whole list of additional categories as well that's not listed in here on this screen. So now, once we've checked out to make sure that our model looks correct, we can go ahead and hit that generate button, and that's going to push it up to the Insight web platform. And then we can begin dialing in our energy factors, or what they call our widgets. And each of these pertain to different construction items, MEP items, solar, and so forth down the list. And what you're seeing in the video example here is I'm actually going through each of these cards, and you've got a graph of a range of least efficient to most efficient systems. And if, like, take for example, your HVAC system that you're using on your building is not listed in one of the dot markers of here, it falls within that range of things. So we're just trying to get a general baseline of understanding of what our building operational cost is going to be. These are not exact factors of everything, but just getting the generalization. That way we can make informed decisions going down the road in the future. So part of this too is once you push your model up to Insight for the very first time, you'll need to go ahead and set up your project. I'm not going to go through every step in here, but I do want to note to make sure to, depending upon which country that you're doing this out of, to set your units. By default, it's set to metric. So we'll want, if you're operating out of the US, you'll want to set that to imperial units. And then also setting that energy use intensity, switching that over to your EUI. By default, they have it set to what the cost, or the annual cost of your, so dollars and cent signs, which I know not all the time that we want to present those type of numbers to the ownership or stakeholders of the project, but getting a generalization of what the EUI of the project to make will make long strides in order to understand your project better and what the energy demands will be. So now from there, we can then start going into the different energy scenarios and dialing in all these different factors of your building itself. So once again, the benchmark comparisons are, we're looking at the ASHRAE 90.1 and the Architectural 2030. Those are built into Insight, and it will tell you where your building is going to reside at, or how it compares with those energy factors. So with that, you've got a list of a whole array of different like widgets or energy factors that you can control between MEP related ones, solar related factors, construction, and operational widgets. So within each one of these cards, you'll see your EUI mean of what your building is going to, energy performance of what your building is going to be, the range factor, once again, that graph, and then you'll see that triangle. It might be a little bit hard to see on my screen right now. That represents where the Revit model is currently at. So like in this example here for the eastern facing walls, or the window to wall ratio for the eastern facing side of the building, it's already taken that value out of the Revit model. So if you have information like building orientation, so if you've already set your true north value, or if it takes the, if you've already got your HVAC system set up in your building, it's going to take those values straight out of Revit, plug it into Insight, and then it'll put that onto the energy graph. And then from there, you can see if you go to the left side of the graph, your building is getting less efficient. And then if you go more towards the right side of the graph, your building is predicted to be more efficient. And then within each of these, the benchmark comparisons, you can see the highs and lows for your energy performance, what the mean is going to be, and then where you sit at based off from the ASHRAE 90.1 and the Architectural 2030. And this is going to be specific for each one of your buildings. So just a couple of notes while you're going through this that we found in our testing is, one is making sure that you, depending upon how you're modeling your building, whether that be massing or modeling, you want to, once again, make sure to have that mode set correctly. If you use the conceptual masses and building elements, it'll pick up from both ends of the spectrum, but sometimes you only want to examine one or the other. So make sure that you have that dialed in. Next is the project phase. If you have phasing in your project, making sure that you have the correct phase set in your energy settings. Otherwise, you'll be running energy analysis on the incorrect phase and getting some odd results popping up in your analysis. Next is the building type. Once again, just setting this to whatever the primary building type of it, and then it's going to take pre-assumptions of that type that's selected and plug that into your energy model. And then design options. Design options aren't always used, but when they are used on the project, making whatever is set to the primary design option is what is the energy model will use when analyzing the building. And then for some modeling aspects of things is one, if you have any building envelope gaps, it's going to register, like in this example here, I've got a large, like a wall missing in my building, and it's picking that space up as shading because it's not fully enclosed, or it's not registering it as a conditioned space of the building. Next is room bounding elements. So I know at least a lot of our designers use floors as site elements. But if you are doing that, just making sure that room bounding check box is checked off. That way it's not being picked up in your energy analysis. And this also goes for if you have, like, let's say retaining walls on your project, or if you're using ceilings or roofs for whatever various methods that are not part of the building envelope that you want to have run the analysis on, making sure that room bounding is unchecked. That way it doesn't pick it up in the while it's going through the process. And then lastly, this is something that we recently discovered. If your building is modeled too far away from the internal origin, you'll get a nice error report email come in saying that it can't run the energy analysis on your building. So paying attention to where you're modeling and how you're modeling is important to the process. But by starting off with these basics, when you're beginning your projects, it's really easy to avoid these issues. So want to quickly get into a quick application aspect of things. This is for a middle school we started testing on. It's currently the project is currently on pause, but the ownership group was interested in diving into energy analysis and seeing how it would affect their building and what factors would be at play to help reduce that operational carbon for their building itself. So once again, we went through, plugged in the building address, selected our weather station. With that too, is you're able to get some basic information like your windrows, speed analysis, your monthly temperatures, and so forth. After we've done that, we've gone through and set up our energy settings as I described before. And then click that create energy model, which then it creates the analytical spaces and surfaces. And we push it up to Insight. Once we got it up to Insight, we were able to start creating different scenarios on Insight itself. And then that way we can then compare those different scenarios depending upon which energy factors that we dialed in, and then see how those EUIs compare to itself, and then making decisions going forward from there. So with that, we were able to then sort our widgets by their importance, determining that the HVAC, plug load efficiency, lighting, the infiltration, and the PV had the greatest impact upon the building. Now, things like construction, like the insulation, whether that be the wall construction or roof insulation, the orientation of the building, those type of things did have impacts, but much smaller scale. And depending upon the stage of your project as well, those already might be built in or baked into the process. And I mean, you're not going to be rotating your building at the end of the project, but you could be adding PV to the project to help boost that operational expenditure for it. So with that, we were able to then set up our baseline. We knew what the HVAC was and our lighting efficiency and our infiltration and our PV. At least for our PV, we've set that to 0 because just starting off with that, like we know that we may not have solar on our project. From there, we were able to then dial in those high impact items, taking that EUI down from a 96 to an 80. And then lastly, what did it take to get to that architectural 2030? So we moved some of those sliders further down to the right of the graph, dialing in, getting the better HVAC system, and then also adding PV to the project. And then that was really able to turn the dial of hitting that architectural 2030 goal. So that way we were able to then go back to the client and say, these type of factors have the most impact, and then we can then decide which direction that they want to go in. But at least we're having those informed decisions at the forefront of the project rather than on the back end of the project when things cost more. So just as a quick overview of things, this can be done at any stage of the project, whether that be in the massing, just getting your basic input on determining what your building orientation should be, how much window to wall ratio, or shading devices that you should be adding to your building. Then like what we do standard is just reviewing basic construction assemblies. We can then compare our operational impacts. And then along with that too, is we're able to report to the AIA DDX. And then if you want to take it a step further, which is not necessary, of course, but you're able to really dial in the building energy report and calculate actual energy values of your materials, your construction, and then diving, like really getting into the weeds of everything. And we're talking about like the metadata and the like digital twin side of things. And then once again, you can report to the AIA DDX for that. So, but that sums up the Autodesk Insight. Thank you.
Thank you. I'll say that was incredibly comprehensive. It really looks like you thought of everything from phasing to design options, right? You know, through the gamut of all. I'll say seeing some of those analysis tools in use rather than just turning off the entire section of them was pretty awesome. And of course, to see that the location is, I mean, that's pretty much the same as we've seen it since like the beginning of Revit, right? So if you're familiar with inputting the location. One question that came up that I also had a question on was on mixed use buildings. I know that we do a lot of that. Is that building type, are you able to specify that by space, or is that something that's based off of the whole entire project?
So yes, you can go in and designate each of those spaces as a whatever type that is, and it gets a little bit more detailed of it. We haven't quite taken it to that extent yet. We're using just a generalized building type to get the overview of our building itself. But yes, you were able to dial into that detail level.
Awesome. Awesome. And seeing, I mean, you know, that you can use it with the mapping tools. While I was digging for some of the, you know, insight tokens, because nothing on Autodesk is free, right? I saw that it also works with Formit, which is cool. So for those of us who are using Formit, so lots of opportunities to use this tool, which is, you know, just wonderful how integrated it seems right into the Revit and Revit atmosphere, just like some of what Seonhee was showing with those add-ins. So that's really great to see that all of this is becoming super easy. Does look like we have a few other questions in there that unfortunately we're not going to be able to get to live, but I'm sure Hans will be able to answer in there. Wonderful questions, you guys. Keep them coming. Next up, we have Jake and Reinhardt from SmithGroup, where I work. Very happy to have them here to talk about some of their tools and some of what they're doing with our PAC team, which I'm sure they'll be able to tell you a little bit about. So happy to have you guys. How are you guys doing today?
Great. Thanks for having us, Dana.
Really happy you could make it. And I got it over here.
Sweet. Sounds good. We'll get started over here. So my name is Jake Chevrier. I've been with SmithGroup a little over a year now. I work in computation design and analytics for, as Dana said, our newly formed team. It's the PACT, or the Performance Analytics and Climate Impact Team.
Hi, everyone. My name is Reinhardt Swart. I'm a lighting and data layering designer, as well as working with the PACT team. So today we want to talk about a couple items. Go to the next slide here. Perfect. Thank you. We do a lot of analysis for building performance, but today we want to focus on the integrated approach and what that means versus the traditional workflow, and really what ingredients you need, the timing, the teaming, and the tooling to make that happen. And then we're going to focus a little bit on translating architecture into data and leveraging this data to help inform design decisions as the decisions are being made. It's not a run and review process. It's more of a informed design space so that we could work at the speed of design. So the traditional design approach goes something like this. We wait for a building to be given to us by the architects, and they ask us to tell us how good they're doing. And we can run that analysis, and that's helpful, but it doesn't necessarily help us to create design decisions for better performing buildings. And so a better way of working would be to flip this process, would be to have the analysis run in advance preemptively, or potentially at the very least at the same time as when the architecture team is designing their building, so that we can inform decisions such as window to wall ratio, massing, the orientation, different programming, all these things from a daylighting and energy standpoint in our particular case, performance-wise, has an impact on the architectural design decisions. To do this effectively, a couple of things need to happen. First, timing. So of course we can be involved at any stage during the process, but most importantly is to be involved at the very beginning when we have the most impact for a little bit of the cost. I think the presentation before us just mentioned that same type of idea, and we want to reiterate that this is critical. The issue is that oftentimes the designs aren't quite baked yet, which is an opportunity, but also a challenge. And so how do we address this in design? We would argue through computation and parametrics, which we'll show you in a little bit here. Next slide, please. Yep. So when you think about the normal design way of working, lots of specialists, lots of smart people informing the design decisions. I would say this is more of an interdisciplinary way of working. I think a better way would be a multidisciplinary or even transdisciplinary approach, recognizing that all of these design decisions actually involve a bunch of specialists and that there's competing criteria often to get to a solution. And very often it's not just one optimal solution, but many other factors in addition to what we see on the screen here.
All right. And forewarned, this is where we kind of get in the weeds a little bit. So you guys are familiar with turning architecture into data. It's the same kind of concept here. We were really trying to take that architectural design problem, what we see on the left, the architecture, link it through a bunch of tools and transform that into data that can create this cyclical loop between analysis and the design problem. So mainly we work in Rhino and Grasshopper, but a lot of our workflows bring that back into the Revit environment for the documentation and detailing. How does this work as a process? It's a 4-step kind of process. We model the design decisions first. We're trying to get ahead of the design process. So we work with the design team, figure out what those parameters could be, come up with a model, and then we simulate all those iterations and create what's called a design space. Think of all the different parameters that we put in, and then we have a multi-dimensional model that we can pull from. We check out the performance metrics. So then we start diving into the data. We look for trends in that data. We look for the best performers. And then once we have those bucketed lists of options, we feed those back to the architect and actually integrate it into the process, into the project. So that first step looks something like this. It's a parametric model. We work closely with the design team to come up with all the different iterations of what they're thinking could be possible within this project. It's impossible to capture everything, but at least we can start abstracting and forming what we call a design space. So if we picture what that looks like, we might have fin depth, window to wall ratio, ceiling height, all these different parameters are creating this massive design space. And this is just 3 here, but you can have multi dimensions to all of these iterations. So then we take those, we simulate all those, and we pull out the data. As we're simulating, we're recording all the necessary data to make that informed design process. Once we have that data, we usually use the parallel coordinate plot, the spaghetti junction, as Reinhardt calls it, over here, where we have the inputs in black. So we're looking at that fin depth again, maybe that window width and that ceiling height. And then we can start looking at that with all our different metrics. And these can be open for whatever metrics that your specific project is interested in. Once we have all that, once we've selected our options, we create a cyclical process where we can take those options and transform them actually into Revit families, curtain wall families, as you see here. So now we'll talk about a use case where we did this. This is a lab building in California. The design team brought us in early to kind of look at window to wall ratio. What type of window? Do they want a ribbon window? Do they want a punch window? Or what we call a vertical window versus a ribbon option? But they're also really curious about a shading technique. They wanted to, it's basically an extruded building, glass facade. So we wanted to create some texture. So we were working with them to help them figure out the shading technique that's also going to bring a performance aspect to the project. Because we like method diagrams, we created a diagram for this, and it played out something like this, where we optimize that floor plate shape. We translate that into design surfaces, panelize those design surfaces into smaller modules. We run the energy and daylight once we have those panels. Then that energy and daylight analysis actually informs the shaping and the shading for those panels. Then we link that to Rhino to Revit, and those get pushed into our architectural facade model here. So I'll walk through those steps a little bit here. We had what we called the wrinkle. This project had, the facade was a wrinkle. So we were looking at optimizing that shape in plan so that we could get the minimum panel widths. This may make it easier down the road during construction, and we won't have all these one-off odd size panels. So we're trying to get ahead of that from the very start of the process. So they gave us the overall shape, and we started using this multi-ejection optimization tool to kind of figure out if there's an ideal setup for that configuration. Once we had that, we got down to 6 panel widths. I think the first one they gave me was at 11 panel widths. So we already reduced the panels right off the bat. Once we have that, we turn it into what I'm calling design surfaces. And then from those working points in the last slide shown here, we can actually panelize those and start looking at it from an architectural standpoint of, okay, is this an opaque panel? Is this a glazed panel? What's the shading technique applied there? And so on.
Yeah, thank you. So we've just talked about the top 3 sort of areas there, steps there. And the next thing I want to talk about or highlight is the energy and daylight analysis, the orange one there in the middle. And I think this is critically important because we are informing the design by pretty stringent daylighting and energy analysis to help back sort of the decisions that the team is making. And we're interested in pretty detailed items. So if you go to the, so all these would inform the subpanels, which we then document, and we'll get to in just a moment. But if you go to the next slide, what we're dealing with is quite a unique challenge because we're dealing with a bunch of parameters and an infinite many solutions, or close to, right? So, I mean, if you look at the glazing options, it's not just the window to wall ratio. In this particular case, it has to do with if it's a ribbon glass, what is the height of the sill versus the header? If it's punched windows, what is the spacing between the punched windows? So those relate to window wall ratio, but they do make a difference as far as daylighting, for instance, glare or view. And so we had to model all those possible combinations. On top of that, we have our shading parameters. So for instance, you look at the shading, spacing the depth ratios of these louvers or these tiny baguettes, spacing depth ratios or dimensions there. So if you sort of layer those on top of each other, you can create what you see on the right there, which is a diagram trying to illustrate all the possible combinations. Each one of these lines starts to represent a possible combination of glazing and shading. And those are the metrics that we're tracking in this particular case. So you'll see here for each facade, we have multiple iterations. And the question for us is, how many of these particular options do we want per facade? Because the facades perform differently depending on the criteria. So what we did is we ran this through Rhino and Grasshopper using Climate Studio for daylighting and Energy Plus for energy. For daylighting, we wanted to maximize spatial daylight autonomy, while for energy, we wanted to reduce the peak cooling load. And so as you can surmise, these criteria oftentimes are competing, and there's not often one optimal solution. It's a compromise between the metrics with other metrics as well, right? Aesthetics, cost, those are design decisions that are real and need to be accounted for. And so this is generally how we simulated the analysis. On the next slide, you'll see a parametric workflow. So we're using Grasshopper, a visual scripting interface for Rhino, to build our geometry on the far left, first box. In the middle is our analysis engine. So there we're running it through Climate Studio and Energy Plus. And we're using Calibri on the far right to iterate through all those combinations and record the data. So the graphic that you see on the right here, behind the scenes is full-scale daylighting, annual daylighting analysis, as well as energy analysis for each of these different options. And what we're doing is we're plotting that, you see on the bottom right there, across different graphs or different metrics to start to understand the different trends based on facade, east, west, north, south, etc. So this is happening all behind the scenes. And the thing that we're interested in is the next step, which Jake sort of mentioned there in his diagram a little earlier, is that each one of these dots represents a possible solution. And so what we're doing is we're mapping all the solutions out for ourselves and for the architect to understand the major trends. So if we look at just the south here, for instance, we have 292 options in the parameters that we chose. And what we're looking at is mean UDI on the x-axis, useful daylight analysis, illuminance, and then peak cooling on the y-axis. Our goal is to maximize the mean UDI while minimizing the peak cooling. So we said if we have an SDA of at least 55%, that's a lead metric, and then a peak cooling reduction of at least 10% or 5%, that gives us a bucket that you see here. It's a more stringent bucket that says these are better performing options. Our goal here is not to dictate the design. It's to say out of all of the options and solutions that we just explored, these are the major trends, and these are the ones that are doing better. Consider using more of these and less of the others. Right? We don't want to tell the architect what to do, but we can certainly inform them in the decisions that we're looking at. So with all those dots, what Jake and I did is we visualized some of the sort of the big four buckets, if you will. You can see on the bottom within those buckets, there are multiple solutions, but we can then go to the design team and have a conversation. For instance, these parameters on the far left, if you use those in some sort of combination, it's less than optimal solution. It's not doing very well, and we would not recommend that. We could do better. Start using some of this glazing options, start using some of these shading options, and now we can increase our daylight while limiting our glare. We could do even better if we go to the best, for instance, and we can increase daylight substantially while maintaining the peak cooling load. And so we're starting to break down the design problem by looking at the parameters and the inputs required to create these different buckets.
So once we have those buckets, like Reinhardt said, we go back to the design team and we say, here's your options. And we kind of come together and we look at what is best. And in this case, for this project, we actually took a mix of these because they wanted to create this randomized textured pattern on the facade, because otherwise it's a pretty simple glass box, besides the wrinkle. The wrinkle is fun. So we started playing with the opaque versus glazed patterning on these facade, and I'm doing this all in Grasshopper. So I'm basically translating each one of these options as an option to be applied to every single piece or every single chunk of facade that's on this project. And each facade has a different shading technique. So all that's done in Grasshopper. And then once we have that applied, we can actually bake those panels back into Rhino. And what this does is it allows the design team to jump back in. Maybe we have a couple people who are comfortable in Grasshopper, but most of the design team wants to work within Rhino or Revit. So the process we developed was to actually bake these panels. And if you click on these panels, you'll actually see that there's embedded properties into those panels. So what we have shown here in the better and best buckets, all those shading options, if it's an opaque versus a glazed panel, that all gets translated into custom user properties for each one of these Rhino panels. So it's our way of giving control back to the design team, because we might be over here in the weeds in our Grasshopper analysis models, and then they don't know what's going on, or they don't know how to interact with it or change a patterning. So we found this to be a pretty good workflow where we can translate that back into Rhino geometry. That way they can jump in, they can click on this, change the panel type to glaze versus opaque. It just gives them another point of intervention, I think is the word that we're using. So once we have that, once we have those Rhino surfaces, we can actually use Rhino inside to bring that over to Revit. So we can open up Rhino within Revit and we can read in those surfaces. All those surfaces have properties, and those properties for each panel can actually drive a custom Revit curtain wall family with all the same matching parameters. So I built this custom curtain wall panel, and it's being placed for every single instance of panel that we have here. The location, the height, the width is placing a curtain wall with those matching characteristics and shading parameters that we developed within the process earlier. So this is our way of bringing it all the way back from, actually, next slide is better for this. So this is our process for bringing it from that first optimized intervention that we did of optimizing that floor plate, looking at the panelization of the facade based on the optimization that we did, running our energy and daylight analysis, feeding that back in and applying those parameters to the subpanels. So we're actually literally informing the design process. We create one more design intervention point within Rhino that the architect can work with before transferring over to Revit. But then once they're comfortable with that, they can bring that all the way back to Revit. We can also do a cyclical loop where in Revit, we can actually read those parameters back in and apply them to the panel. So it does go both ways. And that was important for a design team to be able to cross those borders of the software. So it seems pretty complicated. It's our way of working across platforms. We have Revit, and it's a very great at documentation and all that. And we love doing our analysis within the Grasshopper Rhino environment. So this is a workflow that we've found to help us bridge those gaps between the software.
That was fantastic. And I'll say amazing graphics as well to visualize everything. One question that I had was, what tool are you guys using for lighting analysis within Rhino? Is it built into Rhino, or is it an add-in into Rhino?
Yeah, for daylighting. So there's multiple. We've used Honeybee and Ladybug, which are sort of Grasshopper-based modules. In this particular case, we used Climate Studio, which is a plugin for Rhino and Grasshopper.
I had never seen that logo. So I was like, what is that? I was so ready to post the Ladybug link. And I was like, that is not the Ladybug link.
We've used Ladybug too. Yeah, and Pollination and Honeybee.
Yeah.
Okay, and Pollination and Honeybee. Okay, so I'll put all four of those in the
And I think Climate Studio does have a Revit plugin. I haven't run analysis via that, but they all the daylighting graphics are from Climate Studio.
Fantastic. The other question that we had that's on the mural was, how do you account for multiple design decisions? So, you gave the example of windows, right? How would that kind of play into another design decision that you might want to analyze in this way?
Jake, you want to take that one?
Sure. So if we're looking at windows, for instance, actually, let's go back to I think this slide. This one has multiple design decisions, right? It's what type of window. So you have to come up with a parametric model. You have to think about it. How do you cram all these design decisions into a parametric model? So the first one, we look at the windows, like what's the shape of the windows, and we had to think about how to do this. But basically, we came down to the conclusion that, okay, if we panelize these faces of the facade, then we can run different iterations and different options there. But then we're also applying the shading. So for each one of these glazing iterations, you get a shading parameter on top of that. So you start getting these multi-dimensioned studies. And sometimes we have to reel ourselves back in because we'll get, 1,200 different options. And one thing that we're looking at in the future is actually using machine learning to start doing random forest models to explore that data set and pull out specific models that we should start running versus running all 1,200 iterations. So I guess the answer to your question is you can tack on different dimensions to any parametric model that you're looking at. So just takes
and just kind of playing around with the different iterations, kind of that's what the human aspect is, right? Yes. Like kind of that kind of playing of what's most important and the conversation with the client, the back and forth with that. So
very much. This process shown on the screen right here was in close alliance with the design team. We were talking with them and we were saying, okay, what are you trying to go for with the shading? So there's still definitely the design aspect. We're not trying to replace that. So it's more of working with them and seeing what's possible.
The data-driven decisions, right?
Mm-hmm. Exactly.
Absolutely. Well, thank you guys so much. That takes us exactly to 2 o'clock. We want to appreciate your time. We appreciate the presenters. You guys were fantastic. All of the participants and your questions. I think we were able to reply to all of the questions on the mural. So thank you guys, your presenters, for your ability to do that. And all the participants, make sure you check the mural for those comments to the questions if you weren't able to. And we will see you not next month, but the month after. One last tip that I'd like to leave you guys with is make sure that you are checking your emails, the marketing emails from CAD Microsystems. We are going live in your location we might be seeing you soon in person. So check that out. News to come soon on that. Everybody have a great day.